In previous videos, I showed how to do a static structural analysis of this flat steel bar with a hole and two notches in it. We saw how to refine the mesh, and so we had there's a cantilever, so there's a fixed support here. There's a moment there. There was an axial force, also in tension, and various solutions. In this video, I want to show how to add on a buckling analysis to this. And the way the buckling analysis works is that you do a static structural analysis first with a particular set of loads. Then you add in the buckling analysis, and it factors up the loads, the chosen loads, to see what we'll call what the buckling load is and different modes of buckling. Okay, so we go back to the Workbench window for and here's our project. Over here we have eigenvalue buckling. So eigenvalue, the values are the buckling load. The eigenvectors in this case are the shapes, the buckling shapes. And the more complex the shape, the higher the buckling load. Okay, so we can drag this on top of the project we've done. Now there's various options as you go to drag it. You can create a standalone system, but if you come over this the existing project, you can share the engineering data, also share the geometry, also share the model, not the setup, but you can share the geometry model and then transfer the solution. This is how it terms this to do that. So if you just highlight those and we'll see what it's doing here. So it's using these are grayed out. These are from the structural. It's copied directly. The solution feeds into the setup for the buckling analysis. So we can double click on that and have a look at the setup and maybe make some changes to it. This takes us back into the mechanical. Now, first thing we might want to do is disable this moment. Let's do a simple axial loading. Let's activate or unsuppress the axial force. Now, currently it's a tension force of acting here of 560,000 newtons or 560 kilonewtons. Now we know tension doesn't cause buckling, but Ansys will not object to this. It'll actually reverse. It'll apply a negative factor to change that into. It's probably more. I mean, I'll run that, but it's more intuitive probably to change this into a compression load. But in a real structure, we don't know exactly what direction of the loading in a complex structure will cause buckling. You know, wind blowing from a different direction on a multi-story frame. You know, we don't need to know the buckling shape, the combination of loads that will cause buckling. Ansys will explore the different possibilities. So just to illustrate that, I'll leave it in intention for now. Okay. The other thing we might want to do is just, as we did with the dynamic analysis, to simplify the mesh a bit, because again, buckling is a kind of a global or a macro phenomenon, and maybe we don't. I mean, if we're looking at buckling around here, we might want to refine the mesh, but for the sake of this relatively simple analysis, I'm going to remove that refinement, so delete that. Okay, as we saw with the dynamic analysis, we have to go through slightly. We have to kind of force it to remesh it. Now, one way to force it to remesh is change the size of the mesh from fine to medium, and then click on update, and it will simplify the mesh without the refinement. Just removing the refinement isn't enough. It doesn't seem to pick that up to redo the meshing. Okay, we can go back to the medium and make it a finer mesh. and update that, and we'll see now it'll do a finer mesh. Okay, so which again may or may not be enough around this hole here. We'll see it is actually the whole thing is buckling globally. Local buckling doesn't seem to be an issue here. Now whether that's correct or not, or whether finer meshing would pick that up, would need to be explored. But let's look at the overall, see what it comes up with just based on this mesh. Okay, so we have the tension force acting there. Okay, that's fine. Now, what do we want to look at? If you look at the eigenvalue buckling, it has a pre-stress, the static structural, which is the name of the we could have renamed that, but that's what it's picking up. Okay, how many modes do we want to find? Well, let's go up a bit. Let's try 6. And what do we want to see in the solution? Well, we want to look at typically, it will give us the factors, the buckling load, but we want to see the shape of the modes. Okay, so mode 1, that's fine. And we'll insert total, and we'll do that for mode 2. I'll put all these in now while we're at it. Total mode 3. Mode 4. Up here, insert information total mode 5. And just check the analysis. 6 modes. Okay, so insert deformation total for mode 6. Now the numbers are okay there, but we could actually just shift and click, select them all, right click and rename based on definition, and it'll just put in the word mode 1, 2, 3, 4, 5, 6. Unlike the dynamic analysis, it does not put in the buckling factors here, the eigenvalues, after the analysis has been run. Okay, so now we need to solve this. Now let me see, if we just click on solve, it starts working on the structural. So we see these arrows, these lightning bolts go green, so it's working on that. Okay, and we may need to solve the eigenvalue problem separately. Let's see if it does. We can certainly solve them individually, but we have to solve the structural static structure has to be solved before the eigenvalue buckling can take place. Okay, so this is I clicked the solve button at the top, and it's doing everything. It's now moved on to the buckling analysis. We can see that the green lightning bolts there. The static structural solution is done, so we can display stresses, and those results are ready. It's still working on the buckling analysis. Now let's pause the video and just come back to it. Okay, so the solution is now, everything is done. So we can look at this. So I click on solution. You'll see these load multipliers down here in the bottom right hand corner, and they're all minus, which is understandable because the load it's factoring is a tension load. So to get buckling, clearly it has to switch that to compression, so it scales it by multiplying by a minus number. Okay, and it sorts the modes from the lowest number to the highest number. So the minus 38 is smaller than minus 28. So minus 0.59 is the first mode of buckling. So it's all a little bit confusing. So I'm going to put a simple compression load on it to make it more understandable. But it's perfectly correct in terms of we get the same numbers, the same factors. You multiply each of these factors by 560 kilonewtons, you'll get the buckling load. Okay, so which suggests that the buckling load is around 0.59, 0.6 times 560. So 560 by 0.59. So about 330 kilonewtons compression is the buckling load. And if we look at mode 6, we see that maybe look at it like that, and we can animate it to help see what's happening. Okay, so it's simple buckling about the minor axis. Mode 5 is a second mode of buckling about the minor axis, etc. Okay, so let's just change the load to make the results a bit easier to understand. Okay, so if we go back to the force here, and instead of 560,000 newtons in that direction, I'm going to put in 1,000 newtons for start. So 1 kilonewton. And I'm going to click to change, so I'm going to change it to, so the arrow, you see, as you can switch a direction, so that's compression. I'm going to apply that. Now we have it. Okay, so we're going to have to rerun everything, so we'll click on solve. And I'll pause the video to. Okay, so this time it solved just the static structural piece. It didn't redo the eigenvalue buckling, so we need to right click on that and solve to get it to redo that. Okay, so I'll pause the video again. Okay, so that has taken perhaps 30 seconds or so to do that, and it's back now. So everything is green tick. So let's look at the solution. And now the multipliers begin to make more sense here now. They are, the first mode is the lowest number, 332. So I put in a load of 1 kilonewton and saying we need to multiply that up by 332. In other words, 332 kilonewtons would be the buckling load, or 332,000 newtons. These multipliers are independent of the units that we're displaying down here. You know, they don't change as you'd expect. So they're the multiplier for the unit. Okay, so let's now look at mode 1. And as before, it is buckling about the minor axis. The animation, doesn't kind of make sense, but it's, a buckling is not going to be moving backwards and forwards. It'll go in one direction and it'll buckle. So if we look at that shape, we don't see too much there. But if we look at the y direction, perhaps, so the x and the y direction, that's the end of the plate, and animate it, we see that. Okay, it's reversed around. Okay, so let's look at mode 2, and as before, it's the second mode about the minor axis. Mode 3 is the first mode about the major axis. So if we look at that face on, it's a fairly straightforward, conventional buckling of a cantilever. Mode 4 is, we need to look at that, and that's metric. It's a higher mode, the third mode about the minor axis. Mode 5 is in the fourth mode about the minor axis. Again, nothing much happening around the hole in terms of deformation. It's an overall buckling shape. But the presence of the hole is reducing stiffness here, so it will be affecting the multiplier. And mode 6 is quite an interesting mode. In fact, if we animate that, it's a higher mode about the major axis, but this time if we look at the face on, we see there is this buckling about the hole, so these relatively slender pieces are buckling. So it is a higher mode, as I say, about the major axis, but also incorporating buckling about the around the hole. Okay, so how do these results compare with the theoretical? And theoretical, for such a structure is relatively complex, but there is a well-established theoretical model for the buckling of a solid cantilever. So let's have a look at the theory for that. So for any of the mechanics and materials textbook will give you that the critical load is n squared pi squared ei over 4l squared for a cantilever, where n for the different modes goes from 1, 3, 5, etc. So mode 1, 2, 3, 4, the n goes 1, 3, 5, 7. About the minor axis, the theoretical buckling load for the bar that we have, again, for a solid bar, will be 387, Ansys particularly 332. So, bit of a difference. The bigger difference as we go up the modes, 3,400, 2,200, 9,600, 7,900. The bending about the major axis, the first theoretical is 4,700 kilonewtons. Ansys is giving them 4,200. Okay, so not too bad. Okay, so now the mode 6, what was that? That was the mode, and so I've wanted there were 4 modes about the minor, I have 1 mode about the major. Let me just go back to that and look at mode 6. This is this one, and it's predicting 21,698. So let's just update that table here, 21,698. Now that's much lower, but half the theoretical, and that again, that is, whereas the others are, of the same order. This is quite different, and that's because of that buckling that we saw about the hole. This there is lowering, as you'd expect, the buckling capacity of that. That is a summary of, in a simple case of how to move, to add, to move from a static structural analysis to an eigenvalue buckling analysis. It can take a more complex structure, more complex loads, and it'll factor up all the loads linearly. That's a vector to produce to see parts of the structure buckling. It will work. It will do torsional buckling, lateral torsional buckling, overall Euler buckling, as we've seen here. So local and global buckling of members is picked up by the model. So it's quite sophisticated, and the results, final word, that they need to be treated with great caution. The theoretical buckling and true buckling loads tend to be lower than the theoretical. You can say, probably safe to say that the theoretical is always conservative, because it assumes that there's no initial imperfections in the structure, that the loads are perfectly concentric with the centroidal axis and all that kind of things, are collinear with the centroidal axis. So in reality, there are imperfections in the structure. The loading can be eccentric, off-center, causing moments. And so in general, the conservative, the theoretical buckling is an upper limit for the real buckling. So it needs to be treated very, very carefully.